Okay, Physics Theories, Mr. Thompson here again. We're working on page 100, photoelectric effect number 1, or part 1, and I'm going to do a few questions from part B here. So question 6, let's start with that one. So when incident photons are shown on a metal surface, electrons are emitted with a maximum kinetic energy of 2.60 electron volts. If the minimum frequency to emit electrons from this metal is 8.94 times 10 to the 14 hertz, then what is the wavelength of the incident EMR in nanometers, and what's the type of EMR? Okay, so when we're looking at our conservation of energy and the photoelectric effect, we have the energy of the photon is equal to Ek max, pardon me, plus W. All right, same as the equation I wrote on the previous page. And so what you have here is essentially energy coming in, striking the cathode, okay? So like the photons coming in like this, striking the cathode, ejecting electrons, completing a circuit, okay? So the E total initial and the E total final involves the work function and the kinetic energy of the electrons. Now we're assuming the maximum kinetic energy, in other words, they're very close to the surface, and so it doesn't take much work to be able to liberate the electron from that cathode. Okay? All right, so now when we use this equation, what we want to do is we want to pay attention to what we're given. We have the maximum kinetic energy, so that's Ek max. We have the minimum frequency, the threshold frequency, that relates to the work function, and we're asked for the wavelength of the photon. So let's sub in what we have here. So we have Hc over lambda is equal to Ek max plus, instead of the work function, we'll write Hf sub 0. Okay? Now we can go ahead and do the old Thomson switcheroo. So let's bracket this. Let's do the switcheroo with the wavelength and Ek max plus Hf 0 and rearrange a little bit like this. All right, now, one thing to keep in mind of is you can use Planck's constant in two different versions, okay? There's Planck's constant that is in electron volt seconds. So H equals 4.14 e negative 15 eV seconds. Or you can also use it in joule seconds. So it's important for you to choose appropriately for which one you're going to be working on, or working with. And so in this case here, since I'm dividing by essentially energy, right, these are energy terms, then I have the energy on the numerator and denominator, so the energy is going to cancel off. So I can use either one of the constants is fine. But since I'm given Ek max in electron volts, it's probably preferable that I continue along with the Planck's constant in this fashion. Okay? So I'll show how that calculation will work out. So you have 4.14 e negative 15 times 3 E8 divided by Ek max, which is 2.60, plus 4.14 e negative 15, and multiplied by the 8.94 E14. Okay, let's try out the calculation. Pardon me, bracket there, 2.6 and plus 4.14 exponent negative 15 times 8.94 exponent 14. All right, 1.97 e negative 7, which is about 197 nanometers. Well, a visible light is from, right, 400 nanometers to 700 nanometers. In other words, violet to red, okay? Then 197 would be right to the left of 400, and so in terms of energy, it would be higher energy. And so it would probably have to be in the UV spectrum. All right, let's try one more question here. All right, white light is shown on a metal surface with a work function 1.94 eV. What is the greatest possible speed of the emitted electrons from the metal? All right, so in the case of the greatest possible speed, that would have to be the highest energy. So for the visible spectrum, we'll use the wavelength of 400 nanometers, which corresponds to violet light, because that would be the highest energy and give the electrons the most kinetic energy. Okay, our equation, we're going to use the same one as above there. The photon is equal to Ek max plus W. Now we have the work function here in 1.94 eV. We have this energy for the photon, and so we're looking at the greatest possible speed for Ek max. So I'll rearrange this equation for Ek max. Now energy of the photon is going to be hc over lambda minus, because I'm subtracting W from both sides, the work function. Now, what I'll do here is I'll put in the work function here, and now let's put in one more thing. I like the expression. You can solve for Ek max. That's probably what they're going to do. I'll just do that. You can sub in 1/2 mv max squared and then solve for V max squared. It's a little bit more algebra, but not a big deal. I'm sure you can handle that. Let's just calculate this one here. Now, since the work function here is given in electron volts, and I want kinetic energy, I really want it in joules, not in electron volts. Now you can calculate it in electron volts and then convert it before doing that. So there's really two approaches. I'll try working just in joules for this one. So 6.63 e negative 34 joule seconds, that's the one I'm going to use, times 3 E8 divided by the wavelength, 400, or 4.0 times 10 to the negative 7, 400 e negative 9. Now, when I want to subtract away the work function, I need to take the 1.94 eV and multiply it to get it into joules by 1.6 e negative 19 joules for every electron volt. So let's do this calculation here. Okay. 6.63 exponent negative 34 times 3 exponent 8 divided by 400 exponent negative 9. Take away 1.94 times 1.6 exponent negative 19. All right, I got 1.8685 e negative 19 joules. Now we can go ahead and equate that to 1/2 mv max squared, because that's what kinetic energy really is. Right? It's the kinetic energy of an electron. So let's solve for V max. So I'm going to multiply by 2 straight across. So 2 times 1.8685 e negative 19. And then I'm going to divide by m, which is the mass, 9.11 e negative 31. And then I'm going to square root. Everything's disappeared off the bottom. Let's bring it up there. All right, so we have the following. So I'm going to take that number that I have in my calculator, multiply it by 2, divide it by 9.11, exponent negative 31, and then square root my answer. Okay, I get 6.40 E5 meters per second. All right, thank you very much. I hope you can try out the other problems I didn't do in this section and make sure you know what you're doing.